Well, welcome back, everyone. Before I go here, are there any questions, last-minute questions about the project? No? Problems, but no questions. Okay, well, talk to me afterwards then. I should remind those of you who are only watching on tape that I often answer questions just after class. And so if you're not here, you don't hear them. Okay. So what I want to talk about today is finish. Well, I don't know if I'll finish. I won't finish chapter 6 today. But to continue talking about LU factorization. And so we've got this rather elegant approach. I think it's elegant. I mean, I can say that because I didn't invent it. Of doing a single triangular solve to compute the kth column of both L and U. And it's based on this formula right here, this matrix expression, which is just another way of writing this expression. Okay, so we have the equations for these three terms that gives these three equations that we can then use to compute something. We can compute U12, U22, and L32. And then for permutations, we can use the fact that the permutations can be viewed as if they were applied before the factorization ever began. And so if you multiply to the right a permutation here and swap rows here, you can do the same thing over here to L. Okay, note that permutation does not then apply to U, the U matrix, just to L, because it would be here P times L and P times A. So, and that permutation can then be computed on the fly. And we can in fact take this matrix here, and before U22 is chosen as the pivot, I can take this latter part, these two block entries, this row and this rest of this matrix here, and permute this all I wish. And it doesn't change these equations substantially. I'd have to, for instance, okay, if I were to, I don't have these equations written down, but if we were to do this, permutations, if you take and do a permutation of this, let's see, this would be, there's k minus 1 rows here, because the kth step, the factorization. So here there's n minus k plus 1 rows, right? And so if we permute just these, okay, and leave the top alone, then this equation doesn't change right here. And then the only thing that happens down here is if I do a permutation on this matrix here, I can write that as the following. See, because what I want to do is get instead LU equals P times A. I don't want to get a permuted factorization. I want to get a factorization of the permuted matrix. So if I'm not going to do LU equals A. So this equation has to be modified here. We want to do a permutation here instead. And so one way of doing that, it would be to look at these two equations here and say, well, what happens if we permute those? And we can write these equations down as part of the lower triangular solve as a single block, and it makes it simpler. And then that's as if we're taking the A22 and A32 matrix and just vector and just swapping those around and then doing this work. But in fact, we don't want to do that permutation at that point. We want to do the permutation at the point that makes U22 the largest. And the thing that makes U22 the largest is then, rather than permuting these entries around, this piece, okay, we want to the most stable numerical choice is to make the diagonal entry as big as possible. So to make that as big as possible, we need to first subtract these terms out. So we can take these terms out. Because see, these terms, L21 and L31, except for the permutation, don't impact the magnitude of the values. So subtract these out from the right-hand side. And then that says that U22, then, to make that as big as possible, make this vector here minus the updates, which are here, U12 times this block matrix here. So I can take U12 and multiply it by this matrix L21, L31, and subtract that from A22, A32. And that takes these and puts this on the right-hand side. And then U22 then is just the first entry. This gives us a vector here. I'll call it X2 and X3. And U22 is that top entry. Okay, so if I have any permutations, then I can take this vector and this vector then, after I do the update, and swap here to maximize the magnitude, the absolute value of that first term. Okay, that's partial pivoting. Go down the column, pick the biggest entry. And all it corresponds to is the following. A Gaussian elimination, when you're solving a system of equations with the right-looking method, and you've got these equations you've solved so far. This has been set to 0, and you've saved that in the L matrix. And this is A prime. This is the matrix that you've modified so far. So you're eliminating these equations. And you're at this point, and you just want to go down the column and pick the entry, the biggest magnitude. And instead of using this equation and to solve for that unknown, in terms of these others, we use this equation to solve for that unknown. And the whole purpose for making the pivot large, I should add, is that the update, when you look at if you look at the outer product update, and you ask, well, what happens to this matrix? So this is a numerical digression at this point. We're not really too concerned about numerical issues in this course, just the numbers go along for the ride. But I think it's important to look at this a little more carefully to motivate why it is we're doing partial pivoting in the first place. Because it complicates the code, right? Swapping things around. What happens here is that in the outer product update, let's see, how can I write this? If I just look at an entry in the matrix here, let's see, A, this is J, this is I. So it's AIK times AKJ over AKK. So this update here is what happens to this entry if we're looking at the right-looking outer product, vanilla Gaussian elimination. Okay, take this equation, solve for that unknown, and plug it in these other equations to remove it. And in doing so, that coefficient changes by this amount. Okay. Well, now, what can happen here is, what if this value right here is huge? That's what could happen. That's a problem. If it's huge, you start losing precision. I mean, for example, if I take say a 10-digit number, times 10 to the 10, for instance. Suppose I got 10 digits of arithmetic I'm doing computations on. And I add to this, suppose this is the number pi. Okay. So this is 10 to the 10 times a 10-digit number, and this is 3.14. Okay. And so, when I do this work, I end up with a 12-digit number, 1, 2, 3, 4, and so forth, with a 1, 4 at the end. A 10-digit number, but I can only store the leading 10 digits. I'm sorry, I end up with a 12-digit number, but I can only store the leading 10 digits if I have 10-digit arithmetic. And so effectively, I've just deleted those digits, which you might think, oh, that's not that big a deal, right? They're least significant bits, right? Who cares? Well, I care. You should care. Because what you've just done is you've thrown away all but a single digit of your input matrix. You've got an input matrix here that had pi there to begin with, and now it's 3. And only in Indiana is pi is equal to 3. Right? Do you know that story? For a brief while, Indiana was going to affirm. They didn't really directly say that pi was going to be 4 or something like that, but they said that they were given some patented mathematics, which was, of course, completely bogus, on squaring the circle. Someone was trying to show that basically pi was a rational number. But in doing so, basically, you'd have to allow pi to be, I don't know, 3.7 or something ridiculous like that. I mean, it was just absurd. It was given to the Indiana legislature, and they almost voted on it to approve it. I mean, a mathematician from, I don't know, Purdue or Indiana University, this is in the 1800s, came up and said, no, this is nonsense, and they turned it down. So Indiana did not define pi as 4 or whatever it was. Fortunately, I come from Indiana, so the land of the mythical pi. So you've just destroyed pi, you've destroyed digits from the original matrix. And that's not good, because when you solve the problem, you've just solved a different problem. You don't get the right answer. You don't get the same answer. So you don't want to make this huge. The update needs to be of the same magnitude of the entries that you're updating. And if this is, to keep this from being huge, the only control we have over this is to make sure, one of the controls I should say, is to make sure that AKK is as big as possible. If AKK is epsilon, this is enormous. If it's 0, of course, the whole thing breaks. But if it's a tiny number, that destroys your data. Okay, so you want to make AKK as large as possible. And in particular, what partial pivoting does, if you go down the column and pick the largest value here, then AKK, let's see, this ratio here, AKJ over AKK, is less than or equal to 1. Because AKK is the largest. Did I do that right? No. It's, I'm sorry. This is J. Wait. And this is this is column K. I'm sorry, it's AIK. It's this ratio. I'm getting transposed. One of those ratios. Yeah, it's that ratio there. Not the second one. That looked funny. Because you're making AKK the largest of all the column over all rows I. So this ratio is less than or equal to 1. And that makes sure then that this entry here, if this magnitude of this entry gets added there. So this could be large. That would still be a problem. But at least you've eliminated a large source of the error. Now, it is possible to do more pivoting. Okay. One possible scenario is to go through the entire matrix and pick the largest value in this whole submatrix. Well, there's several problems with that. One, we need a right-looking method. See, the left-looking method doesn't have this matrix yet. It's not computed. It's not updated. It's not determined. So we don't have an alternative if we're using a left-looking method. It constrains our pivoting. So different matrix factorizations give you limits as to the kind of pivoting you can do. The other problem too with column pivoting, you see, what do we find out with QR factorization? The QR of a matrix A times P, R and Q are an upper bound on the non-zero pattern of L and U, and in Chapter 7, which we haven't looked at yet, the field-reducing ordering on a Cholesky factorization of A transpose A will give us a good column ordering that reduces fill-in the matrix U. So that's a good strategy for reducing fill-in. And it becomes like a game. You want to pick a column ordering here such that the row ordering via partial pivoting does as least damage as possible in terms of fill-in. See, because this partial pivoting does not consider the fact that, well, what if this row is dense? That's actually not a good thing. So there's a trade-off here between partial pivoting and numerical accuracy and fill-reducing ordering. What if the largest entry is in a very dense pivot row? Ooh, that's not good, is it? But you see, QR factorization will already accounted for that because it says that, well, hey, the pivot row is the set union of all possible pivot rows. That's what QR factorization says. And if we minimize the worst possible damage from that, then we at least try to minimize the worst possible damage from this, LU. But so if I just arbitrarily go to any column and grab it and slap it on there, then I've destroyed this upper bound. I'm not obeying this upper bound. So we have to use a different pivoting strategy, reduce fill. The other interesting thing that happens with this trade-off between fill-reducing ordering and numerical stability is that they don't always go, improving one doesn't always improve the other. So they're not so tightly linked. In fact, it's almost perversely the case that if you were to do complete pivoting, this is complete pivoting, right-looking method, just go and pick the biggest value here. And if you pick the biggest value here, this means that this ratio here, AKK, is bigger than both AIK and AKJ, both together. Okay, so then this ratio, each of this, that ratio and this ratio is less than 1. And the update will be bounded, let's see, by, the bound gets a little more difficult. But it's bound, it is a much tighter bound. But if you just blindly pick the largest value, you get a lot of fill-in. When you get a lot of fill-in in the matrix, you have more work to do. Every time you do work on a matrix, every time you do work on a matrix or on numerical values, each operation you have to throw bits away, right? Because you can't. I mean, you have a floating point representation. You do work on it. You multiply two numbers together, you get a number that's twice as many digits. You have to chop it off and throw half of them away and round to the nearest, 64 bits or whatever, 54 bits, whatever the mantissa is on your computer. So every time you do an operation, you're throwing information away. And so if you have really, really high fill-in, even though you're trying to use a very, very, very careful pivoting strategy, you may get gross fill-in, enormous amount of fill-in. You do more work, you get more round-off error, and you actually get a numerically worse answer for getting higher fill. So you see the symbolic and numeric fight each other. And they feed off of each other. And this only happens in LU factorization. It doesn't happen for Cholesky. Because see, for Cholesky, any pivot order is numerically satisfying. I mean, it just will not cause an error. I mean, if the matrix is symmetric, positive, definite, any permutation is numerically just as good as any other. With QR factorization, it doesn't matter what the row ordering is. Okay, it doesn't matter what the row ordering is, you're going to get the same effect. Now with QR factorization, the column ordering does affect the numerical values of the result, especially if you have a rank deficient matrix. Okay, that's a different issue. But this kind of numerical sensitivity only happens for LU factorization. And so we have to have some strategy. You see, with Cholesky, we didn't look at numerical pivoting at all. With QR factorization, we didn't consider the numerical values at all. We just said, forget it. The numbers just go along for the ride. And the symbolic work there was no feedback from the numerical work back into the symbolic. It had no effect. That's different for LU. For LU, we have to say, well, I want to swap and put the thing up here. And see, when you swap, things happen that are different, that are within the bound for what you predicted from QR, with you swap rows, but things can change. I mean, if you're down here and you say, well, I want this value, this row or this row, what if, these pivot rows can be different? And symbolically, when you did the symbolic analysis, you can't tell the difference between these two rows. But when you choose this one versus that one, that depends on the numerical values. And depending on what you do, there's another row down here, this entry will either fill in or it won't, depending on what you choose. That's an entry that's in the matrix symbolically now that wasn't there before. Now the QR upper bound would account for the possibility of these entries, but as you do LU factorization, you don't really know if they're going to become non-zero or not. Okay, when I say non-zero, I mean ignoring numerical cancellation. I mean symbolically non-zero. An entry in the data structure, an entry in the combinatorial beast that we're trying to get a grapple on. So LU factorization is a challenge in this regard. It adds this extra feedback between numerics and symbolics, which makes it intriguing and makes it an interesting problem and a challenge. So that's what pivoting does. And I've already explained this. So now let's look at the code. Let's look a little bit at so I looked already a little bit at the MATLAB prototype of this. And so, but I didn't give you this derivation over here. So this derivation says that, okay, I can do the triangular solve first. This triangular solve from the previous slide, that funny lower trapezoidal matrix with the identity slapped on. Okay, that's this thing. And here I actually slap on the identity explicitly. I mean, this is very inefficient, right? You wouldn't actually try to solve this. This is a MATLAB working prototype for the actual algorithm. It's a very useful kind of code to write. I mean, it illustrates the algorithm very cleanly and succinctly. But you wouldn't be able to actually execute this efficiently. Then you get this column here, this column X, and then that defines, without anything at all, the what is it? The U1, 2 vector, right? This is the column of U above the pivot. And then below it now, here's our partial pivoting. This is looking at the matrix here, in the vector X in positions K through N, K through the end of the vector, and saying, well, let's pick the biggest one. So the max function in MATLAB does this, max of absolute value of X of K through N. That gives two things. It gives the actual absolute value A, which we throw away, we don't need. That will be the absolute value of this pivot entry, but I don't want the absolute value. I want, when I actually do the number, I want the sign on it as well. But it also gives the row index, and this offset happens only because MATLAB doesn't know, in fact, the point here. This is a vector of length, what, n minus k minus plus 1 or something. So we've got to shift that row index. The max function gives two outputs, right? It tells you the value and the position that it occurs, but the position has to be offset by where we are in the matrix. So that's what this is. And then this actually physically swaps. This is kind of cool notation in MATLAB, right? If you've seen this, if you think about what this is doing, it's taking this 2 by n matrix, right? Row k, row I, and it's slapping it into row I, row k. That does a swap in MATLAB. Do you see that? You don't have to actually, copy it into temporary and put it back. One line. Very elegant, very inefficient on sparse matrices, of course. Same thing happens to the permutation vector, which starts out as identity. It gets, so we have to log the permutation, and that happens there. We have to swap the entry in the X vector. So here's the actual swap, and then there's the rest of the work. There's the pivot. This is kind of pointless, I guess. I don't know. This would not have had to have been done, except that what's happening? Except that I guess this swap would have mangled this value. So there's the implicit unit diagonal, and then there's entries below the diagonal, and there's the division by the pivot. So this gives us the MATLAB prototype with this partial pivoting plunked in there. And the key thing here is that the column ordering doesn't change. The column ordering is as it was from the beginning, 1 through n. So it could be 1 through n, but of course for the sparse case, it could be coming from a fill-reducing ordering from the QR factorization. Because I could have I need a different, here's a column permutation from a symbolic QR, from fill-reducing ordering from chapter 7 that will say, hey, don't do it in that ordering for the columns, do it in this column ordering, and that'll tend to reduce the upper bound on the fill-in. But the row permutation here is based solely on partial pivoting. So it is really a game in the theoretic sense. The fill-reducing ordering says before the game starts, I'm going to pick, so it's a game between two opponents, and the game is this, in a theoretical sense. The fill-reducing ordering says I'm going to pick a column ordering so that you, the numerical factorization, can do the least amount of damage possible. So pick the column ordering here such that LU factorization with arbitrary partial pivoting, because the first player in the game doesn't know the numerical values. So the first player picks the column ordering to minimize the worst case damage that the partial pivoting can do with the numerical values during numerical factorization. So it's so you want to choose a move in this game, if you will, theoretically, I mean, in terms of game theoretic, you know, player one wants to choose a column permutation that bounds as much as possible the worst case that the numerical damage can do in terms of fill-in. That's not described here. What's here, we just go from left to right. So this is the numerical work, if you will, where the column ordering would have been already defined. But in the sparse algorithm, what's come up next, then we take that column ordering as input to this factorization. So it's going to effectively say, well, I'm not factoring A, I'm factoring A times to the permutation to the right. And so that'll just simply affect the way and we'll do this by looking at a view. We take in a column permutation, and it'll call it lowercase q, the vector lowercase q. And that will just tell us, well, where is the first column of this permuted matrix? It'll just reshuffle the columns. We'll leave the A matrix alone, but we'll say, well, oh, this is the first column, and then this is the second, and that's the third, and so forth. We'll just look at it through a lens. So otherwise, then the rest of the matrix is the same. And then it doesn't affect the L and U matrix at all. Okay. The other interesting thing to notice, and I think I exploit this. Let's see. Yes, I do. Is that this step right here just says, well, grab the first k-1 entries out of the X vector and slap it into the U matrix. Okay. At this point, remember, the L matrix, we're going to leave the row indices in the old space, not the new space. A row index 42, if I find row 42 in this L matrix during factorization, then that's not row 42 of L. That refers to row 42 of A. So whatever row 42 of A is, it'll be moving around. And so I need a fixed name for it. So I'll just call that row by its name in the original A matrix. And then when everything is done, the permutation is finished, the row permutation is finished, I'll fix that up with L. Now here it's just doing it on the fly. Okay, but this is too complicated. We can't do this. Is too hard to do for the sparse case. But for U, it's different. Not you personally. For the matrix U, okay, at this point, we know already the first k-1 pivot rows. And those aren't going to change. So this is the only place that U is modified. Well, there and here. And at this point here, we know the kth pivot row. So whenever we're touching the U matrix, we know all its row indices in the new space, the row corresponding to rows of U, not of A. And so at that point, we might as well put in the new row index. The other thing to observe about this is look to see where else U appears. U, the matrix. And no, that's not Keanu Reeves. Is that how you pronounce his name? Neo in the matrix. U, the matrix. Okay. It only appears here and here. It doesn't appear in the triangular solve. It's just a write once data structure. You just stick it there and forget it. Stick it there and forget it. Toss it over the fence to the U matrix and then forget it. You don't need it at all. L, on the other hand, is being written and then reused. Written and reused. The A matrix, if you look at the data flow for the A matrix is only being read in one column at a time, from left to right. Right here, AK. That's it, isn't it? Yeah, this is the only place where the A matrix appears, right here. That's it. So A is being read one column at a time, from left to right. U is being written one column at a time, from left to right. Written and then forgotten. L, on the other hand, is very dynamic. It's being written to one column at a time down here. But then it's a left-looking algorithm. So at each step here, this triangular solve says, well, let's go back to all of L and do the sparse triangular solve. So now let's look at the details of the code, and that'll reveal some other interesting algorithmic issues. And really, again, that's why we're looking at the code. We're not looking at the code just because, hey, it's pretty code, because it's very concise code, but it's not as pretty as I might like to make it if it wasn't trying to be squeezed tightly to fit into a book. Okay, but the purpose here to look at the code is to get insight into some of the combinatorial issues and the algorithmic issues that you really can only get at if you look at the details. So let's look at the details. So we're passing in there's another. This is a twist on the partial pivoting. I'll explain when we get there. We're passing in the symbolic QR factorization, which might not actually be a QR factorization. It might not be from the symbolic QR. We can instead, if we want, just pass in, because the only thing we use from this are two things: just an estimate or an upper bound here of the number of non-zeros in the U matrix and in the L matrix. And we also have the column ordering. I'm sorry. So this S gives us three things that we need. And we really only have to have one of them. And that's the field reducing ordering Q. These right here could be wild guesses if we like. Okay? If I do QR factorization and have a bound, I could use that. That's an upper bound. And so that means I could use a static data structure later on, and I don't have to make my L and U matrix bigger. But I already have code that can say, well, you got a matrix that doesn't have enough non-zeros in it, just reallocate it, make it bigger, right? We already looked at that piece of code. It's just the dynamic table approach. If you run out of space, double it, right? And so we can do that with L and U easily because we're just growing L and U from left to right, column by column. So it's a very simple data structure. There's just a dynamic table. So this right here can actually just be an estimate. So that's the only thing we get from the symbolic analysis. Then we need some workspaces, a double precision workspace for the gather scatter. We need workspace for the depth first search, right? This is going to be used in the sparse triangular solve. We're going to need a vector, let's see, for the stack, and another vector. I think the DFS used 2n workspace, if I recall. Anyway, that's there. And this allocates the numeric result. This is a constant size. This is just a struct. And we're going to stick in it, then, the L and U matrix and the P inverse. This is the row permutation. So this numeric factorization has the L matrix, the U matrix, and the P inverse. And the L and U matrices are spallicked to be just n by n with whatever many non-zeros we can fit, we think we will have. And then x gets set to 0. And like I said, I could have done that with a calc here, but I was worried, and so I didn't. I don't calc any double precision workspace in the book, and this is the only place I think I actually need to zero out double precision workspace. I don't think I needed to have done it until this point, because I don't think the matrix. I think the matrix multiplication, for example, if I recall, didn't need a calc there either. I think this is the first calc I need of double precision workspace. I could be wrong, but I think that's true. I'm curious now. I'm going to look it up. Oh, no. Yeah. So if you look at, say, at the matrix multiply on page 18, okay, the x vector here of a double precision workspace of size m, it's comparable to this workspace here, is only malloc, and then it's not initialized. Because I know whenever I touch it, those entries will then be handled by the gather scatter function. So the workspace is uninitialized, which is the best way to do it. Right? If you have a big workspace of size n can be enormous. Going through that and setting that to 0 is not a trivial thing to do. Asymptotically, it's not a problem, but performance-wise, I worry about those things. Okay, and it's little things like that make a big difference. But here, I decided I needed the workspace zeroed out I could have gotten away without it, actually. I'll explain. Okay, so now, so here's the bulk of the work. Okay, now we're getting into the real algorithm. The stuff on the previous page was just, mechanics, right? So this is important. This is our inverse row permutation. Okay, and we have to have it inverse because we're constantly going to be doing mapping from the old space into the new. So we need a P inverse of old equals new kind of function, right? We need to put in, use I for old and always use K for new, right? So I'm very careful with my indices, with my names of things. So this is I referring to a row I in the A matrix, and I'm saying that row I in the A matrix is currently nowhere in the resulting matrix because I don't yet know anything about the partial pivoting decisions. So when I pick a pivot then, if I pick row 42 as the third pivot, then P of 42 will be set to 3. Okay, so P inverse, let me write that down. So if I had P of K equals I, this is new and this is old. If I have P inverse of I equals K, then this is new and this is old. By old, I mean a row of A. By new, I mean a row of L. So it's this that I want. Okay. And then I initialize the column pointers of L because I'm going to need to use that in the depth first search. And, I meant to go back. I'll have to pull up from the previous chapter, I think 3 slides. I meant to stick it into the notes for chapter 6, so I don't have to do that. But anyway, we'll have to look at this code here again because we've done this before. So the first thing that has to happen then is that triangular solve. And this is where the bulk of the work happens. The rest is just clean up, sticking the results where they go. ln z and un z are now going to keep track of how many non-zeros I've got in the L and U so far. You see, and that's kind of handy because L and U are growing from left to right. So I'm just slapping the columns into the matrix, and then the kth step, I just slap in the next column. And this is all empty space for both L and U. So that it's a very simple data structure then. And what that means then is that I can do a very quick check. I can say, look, how many non-zeros do I currently have in the matrix, ln z? Well, what's the worst case that could happen? I could add into the L matrix up to, well, I just cheat. I could have reduced this to like n minus k or something like that, right? This is a bound on the number of non-zeros I could append to this matrix. And n is also very crude. I could have put in k here just as easily. And I don't yet know how dense these columns are going to be, but this is certainly a nice bound. And if I'm getting, the reason I just left this as n is because if I'm getting that close to the end of the matrix, well then it's probably going to happen on the next couple steps anyway, right? I mean, n is not much extra slack space. All right, so fine. If we may run out of space, if either of these is too large. So if this number is too large compared to the actual count of the space that I have, well then we better call Sprialic and double it. So there's the dynamic table, plus n to give us yet another make sure then that ln z plus n. This plus n ensures that now this statement is false with the revised nz max. And there's twice, so that gives us the dynamic table data structure. Anyway, so if either of these conditions fail, so if this is false, then this kicks out and the condition fails. If this is false, then it kicks out. But if this is true, then this had better be returned as false. And Sparse, no, is true, I'm sorry. So I negate that. In other words, you call Sparse, if it fails, then this condition becomes true. And if it becomes true, that means you've run out of memory. Right? So you try, if you don't need to get more space, nothing happens. But if you need more space and you can't get it, then this condition happens, and we just return. And the return then does several things. With the return value of 0, it returns a numerical object n, which is null. It's freed. And the workspace is freed. So it just frees everything. With 0, it's a fail return. So it frees all these three things and returns null to the caller. So it's a one-line cleanup, which is kind of handy. Okay, so suppose that succeeds, or suppose that we don't have to worry about that. It doesn't have to happen. Then, well, this is kind of awkward. This code may have reallocated the L and U matrix. I don't have any indication of that coming out, because whether or not I had to call these Sparse functions or not. And so I just reacquire the row and the row indices and numerical values of L and U anyway. So now I'm ready to do, now I've got my LU matrices fit with enough space. So now I've got to do the triangular solve. And the triangular solve, you remember from the previous slide, the MATLAB code, we have to take the kth column of A as our input to the triangular solve. So what is the kth column of A? Well, it's either column K or it's the kth column of the permuted matrix. So that's all this does. Which column do you want? Do you want the kth column? Well, if Q is null, that means identity. So if Q is null, you just want the kth column. Otherwise, you don't want the kth column. You want the kth permuted column. And that's what this gives as on input. This is the column ordering on input. So now we have the proper column of the A matrix, and that's what's inputted here. So in the sparse triangular solve, we're given an L matrix where all the column pointers are defined, including zeros here, which initializes the space just to be safe. So columns that don't exist yet will have a 0 as their column pointer. And this is the right-hand side, the column call of A. And then we pass in the workspace, where we're going to do the gather scatter X, numerical workspace. And this is the stack right here, the XI space. And it's also going to be the list of row indices on output, if you remember the triangular solve. And now this is something we haven't used before, is this row permutation. Because you see, we need to know, remember that this L matrix here, okay, the L matrix actually looks like this. Well, to be precise, it looks like this in the data structure. This has to be implicitly identity. So I have to know when I'm at a particular column, how do I know whether or not this is a good column or not? And we do that by looking at that row permutation. But we also have to say, well, if I'm at a column that's got stuff in it, and I get out a row index I, okay, I have to do a remapping here in the sparse triangular solve. Because the row index I has to be used uniformly. This is old. And I have to do that consistently, because if I have a row I here and a row I here, they're different, right? This is a row at some previous step, and this is a non-pivotal row. But in the triangular solve, we have to do this numerical gather scatter into this X vector. So I have to have a consistent name for these rows. I know what both the new and the old both are for this row. But I don't know what the new row index is for this. You see, that means I have to use the old row index to do my gather scatter into the X vector, because that's the only thing I know consistently for all possible rows in this matrix. However, there's a remapping that has to happen when you're doing a triangular solve and you're inside this L, and you want to, okay, I'm at a node K, and I need to do I need to go from, say, K1 to K2 from one node of L to the next. Those nodes correspond to columns of the L matrix. Remember in our sparse triangular solve, which we did eons ago. So there's this non-zero right here means there's an edge from K1 to K2. Well, this is L K2 comma K1. But now think about this. I've just said that I can't afford to go changing this row index all over and over and over again. This row index in particular only has one name because it's not been chosen yet as a pivot. I do not know at what point it will be chosen as a pivot row. That will define, like if this is K3, I don't know K3 yet. Could be here, could be there. I don't know where it will eventually be chosen. So I have no name for this except the row corresponding to the row of the A matrix, so the old I. So for K2, I don't have K2 in my data structure. If I go look at column K1, I grab a row index out, it will not be K2. What will it be? It'll be the old. Okay? It'll be the old row I. It'll be that I such that P inverse of I is equal to K2. Because row I then would have been chosen at the K2 step in the factorization. Because see, I'm working right now on the kth step, which is here. I'm computing the kth column of L. K1 and K2 are less than K. They're in the past. So I've got this row index here, and I need to know both its old and its new name. Because I need to know its old name because that's what I'm going to use to gather scatter into this X vector. But I need to know its new name because I need to know, well, what edge do I traverse to go from K1 to K2? I need to get K2 as well. K2 is the new name. The old name is I, and the new name is K2. So it's the row permutation that tells me what column to go to. So if I'm at column K1 in L, and I need to do the depth first search to say, well, what are your outgoing edges? I see an I, and I say, oh, no, you're not I anymore. You're K2, which is the PINV of I, the P inverse of I. And then that tells me who to go to next. That's my adjacency. So you see, that's the mapping that has to be done. We have to take a column index, go down and find its adjacency. We get a row index out. We got to map it through P inverse to get K2 to find out which column to go to next. Do you see that? Now, what happens with this P inverse if we're down here? P inverse of I is equal to what? -1, which says, oh, you're not chosen as a pivot yet. Okay. Well, what kind of column of L will that refer to then? Nothing. So if I see a row I for which P inverse of I is equal to -1, then this is some K3 or something. I don't know what the name of this node is. It's not defined yet. It's going to be here, or it's going to be here. Who knows where it's going to be? It doesn't matter. Whatever it is, the only thing I need this node for, two things. I need to know, first of all, that it has no outgoing edges, because we're in the identity, the implicit identity part of the L matrix. That's one thing, but so that I know that implicitly. So if P inverse of I is -1, I say, I don't need to look at you in the data structure of L because you're not there and you don't have any edges anyway. Done. The other thing we need to know is still, though, we need to use I for the gather scatter into X, because remember, that's the only consistent indexing we have into this X vector, the gather scatter. And in terms of storing, also we need I to put here in terms of the row index. See, when I compute the kth column of L, symbolically in the depth first search, I get a list of row indices. But those row indices, I don't know their new name, I only know their old name. So I need that I to store into the kth column of L. I don't have the new name because P inverse of I is not defined. I need to know the row I to put into the data structure, and I need to know that P inverse of I is -1, so the node corresponding to it in L has no outgoing edges. If P inverse of I is not -1, then this is another column of L, and it may have outgoing edges. It may, in fact, also be identity, but that's a defined part. So we have there's this separating line here. It's kind of handy in the chalkboard. This is a defined part of L, and this is the implicit identity. Okay, so that's what the sparse triangular solve is going to have to manage. And we didn't have to do that before. So I'll cover this then on Wednesday. We'll look more specifically. We'll do a subroutine call here, plunk into the sparse triangular solve, and we'll look more carefully at what this does when the P inverse is present, which we didn't do before. So, see you then.
Oh, so for K3 we just know that is undefined and we skip it?
Yeah, it's undefined. K3, the question is, what about K3? Well, K3 is undefined. In terms of the depth first search, it's skipped for any further traversals. But the fact that we were able to visit this node is important because that means that when you in the depth first search, the result of what nodes you visited gives the non-zero pattern of the result X. We don't know the name of that position in the new space, but we're not keeping track of that. We're only keeping track of these names of these nodes in the old space, and I have the name for that. It's I. You see, so I have the pattern of the column I in the old index space. Here, I don't need to know the new for any of these nodes, actually. And if the new space is not defined, if it's -1, then all I need to know is it has no outgoing edges. So it needs no further traversal because they're not edges there anyway. So there's one piece of that node that's not defined, but I don't need that information yet. That's the key thing. So that's what the sparse triangular solve is going to have to handle, that little twist. Once we handle that little twist, we can do the triangular solve with this funny trapezoidal matrix, where we have L, this funny matrix here, L with the implicit identity, and added on top of that the lens here that we're looking through this matrix of the row permutation. So that's what the sparse triangular solve is going to have to manage, this implicit identity and the row partially defined row permutation. Okay? All right. Good question. Thank you.